All right, question 44. We have these two cell phone towers, A and B, and what we know is that they're 10 miles apart. So one way I could picture them is on the coordinate plane. We'll throw A at the origin and B out here at 10, 0. What we're trying to do is build a new tower that we're going to call S, and we need the distance between S and A to be 2 miles greater than the distance between S and B. So one possible location for S would be right, here, I guess, at the point 6, 0. This distance clearly 6, this distance clearly 4. This is 2 more than this. But this isn't the only possible location for S, maybe S naught, sure. There's infinitely many places we could put S satisfying this criteria. And what the question is if we consider all the possible locations for S, would that give us a branch of a hyperbola, a circle, an ellipse, a line, or a parabola? Well, first off, we can rule out a couple of these pretty easily. It can't possibly be a circle or an ellipse, because if it were a circle or an ellipse, whether this point is just some arbitrary point on the circle or ellipse, or the point on the circle or ellipse with the greatest or least y value, there'll be some y value for which there are two different x values on that circle or ellipse. And if the distance from A to the leftmost of those 2 points is 2 more than the distance from B to the leftmost of those 2 points, the distance from A to the rightmost of those 2 points can't possibly be 2 more than the distance from B to the rightmost of those 2 points, because the rightmost of those 2 points is closer to B and further from A than the leftmost of those 2 points. Just from kind of thinking about what a circle or an ellipse looks like, you can probably rule out answer B and C pretty easily. You could probably also eliminate a line from being the solution. If you sketch a vertical line through this point S naught and convince yourself that any point that's closer to B than it is to A would have to fall to the right of this vertical line. And because there'd be possible solutions above or below the x-axis, these 3 points can't possibly all be collinear. What I'm saying is without a lot of analysis, we could reduce the number of solutions down to 2. The answer is either going to be A or E. But maybe you don't feel like guessing. You want to know which of these is the right answer. Well, there's at least 2 ways that come to mind for me to figuring it out. The first one would be significantly quicker, but it would rely on you knowing the definitions of a hyperbola and a parabola. By definition, a hyperbola is just the set of points whose difference of distances to 2 fixed points is constant. Contrast that with the parabola, which is the set of points that are equidistant to a single point and a line. That single point is called the focus, and that line is called the directrix. Whereas in the case of a hyperbola, the 2 fixed points are called the foci, just the plural of focus. By just reading these 2 definitions, maybe you can see that the situation described up here is exactly the definition of a hyperbola. The 2 fixed points, aka the foci, are just points A and B. The constant distance is just 2. Because we only want the points that are 2 closer to B, not 2 closer to A, we only get one branch of this hyperbola. The answer to this question, kind of by definition, is just A. If you know this definition, this is a 15-second problem for you. You mark A and you move on. And while that's clearly the optimal scenario, I think it's worth spending a little bit more time on this problem, showing how you could solve it algebraically, figuring out the exact equation of the hyperbola, not only because you might not know these definitions, but also because a different question might require you to do such things. So first off, a quick review on conic sections. There are 4. We got a circle, an ellipse, a parabola, and a hyperbola. They're the 4 shapes that arise by taking different cross sections of a circular cone. The standard form of the equation of a circle is x minus k squared plus y minus h squared equals r squared. This is the circle centered at kh with radius r. Very similar to that is an ellipse. Its standard form also has an x minus k squared and a y plus h squared, where kh again represents the center. However, now instead of the sum being equal to r squared, it's just going to be equal to 1 because there's kind of 2 different radii, loosely speaking. Maybe we'll call them a squared and b squared. A kind of represents the radius in the x direction and b the radius in the y direction. I know radius isn't the correct term there, but I think for most people that's the easiest way to think about it. Just like we have these definitions up here for a hyperbola and a parabola, there's a similar one for an ellipse. The ellipse is just the set of points so that the sum of the distances to any of the points from 2 different foci is a constant. And really with this equation, I'm assuming those 2 foci either have the same x coordinate or the same y coordinate. You kind of tilt your ellipse if you really want to make this thing general, but then these formulas get kind of ugly. Same idea with the parabola and a hyperbola. You could make these really general. But for the purposes of this test, we can just assume that our parabola has an axis of symmetry parallel to the x-axis or parallel to the y-axis. You're probably more familiar with the ones that have an axis of symmetry parallel to the y-axis. Maybe you're thinking y equals x squared, and that's fine. Or if you want to be a little bit more general, you could make it x minus k, maybe squared plus h. And now the vertex is at kh. If instead of opening upwards, we wanted our parabola to open to the right, we kind of just shuffle the letters around, get x equals y minus h squared plus k. That leaves our vertex at kh. If we want to open downward or open to the left, just toss a negative out in front here. It'd leave the vertex unchanged. Finally, a hyperbola, it's almost identical to an ellipse. The only difference is instead of a plus sign, we put a minus sign in between the two terms. So we got x minus k squared over a squared minus y minus h squared over b squared equals 1. Unlike addition, which is commutative, subtraction is not. So the order that we write these two terms matters. If you write the term with x's in it first, it's going to open left and right. If you write the terms with y's in them first, it's going to open up and down. So with all of this information in mind, we can go back to the problem at hand and consider some arbitrary point, maybe I'll call it S1, whose coordinates are just x and y, such that the distance to b is 2 less than the distance to a. Maybe I'll call this d sub b, and I'll call this d sub a. Sure. Well, it's pretty easy to calculate these two distances. Just draw some right triangles. The distance to a is going to be the square root of this length squared plus this length squared. This has length y. This has length x minus 0, or x. So the distance to a is just the square root of x squared plus y squared. Using the same logic, we can figure out an expression for the distance to b. This length is again y. This length is 10 minus x. So the distance to b is the square root of 10 minus x squared plus y squared. What we're told in the problem is that the distance to a is 2 miles greater than the distance to b. So if we plug in these expressions for distance, we get that the square root of x squared plus y squared is equal to 2 plus the square root of 10 minus x squared plus y squared. It's not immediately obvious which of these forms this equation is equal to, but if we could figure out which one it was, we'd know which conic section we have. We'd also have an exact equation for that conic section, so we could answer other questions about asymptotes or vertices or foci or whatever. So let's do it. You might notice that we don't have any radicals down here, so maybe a good strategy is to get rid of the square root signs. One way to do that is to square both sides of the equation. Note that both sides of the equation are positive, so we don't lose any information by squaring both sides. We get x squared plus y squared is equal to, squaring this side, kind of think FOIL, you get 4 plus 4 times the square root of 10 minus x squared plus y squared, plus the square root of 10 minus x squared plus y squared squared. In other words, 10 minus x squared plus y squared. Things look kind of ugly, but conveniently the y squareds cancel out. And if I expand 10 minus x squared, I get 100 minus 20x plus x squared. And I can cancel out that x squared and this x squared. What I'm saying is when all the dust kind of settles, I get 0 is equal to 4 plus 4 times the square root of 10 minus x squared plus y squared plus 100 minus 20x. I still have a radical, so maybe I'll isolate that to get rid of it. Add 20x to both sides, subtract 104 from both sides. Leaves me here. You could square both sides at this stage, but since you don't have a calculator, you might want to keep the numbers as small as possible. And one way to do so would be to divide both sides by 4. Give me 5x minus 26, because 25 fours is 100, is equal to the square root of 10 minus x squared plus y squared. Now I can square both sides of the equation and get 25x squared minus 5 times 2 times 26, so 10 times 26, so 260x, plus whatever 26 squared is equal to, equals this side squared. Well, the square and the square root will cancel out, and in the interest of later combining like terms, maybe I'll expand these parentheses to get 100 minus 20x plus x squared plus y squared. If I move everything over to the right side of the equation, I got 0 equals y squared minus 24x squared. Let's see, plus 260x minus 20x, so plus 240x. And then plus whatever 100 minus 26 squared is equal to. I don't feel like calculating that, so I'll just leave it as is. At this point, you might be able to figure out which of these forms we have. But I love algebra, so I'm going to keep going. I'll leave the y squared alone. And then for negative 24x squared plus 240x, I'm going to factor out a negative 24 temporarily, leaving me with x squared minus 10x. And I'll leave this mess alone, 100 minus 26 squared. The reason I did that is now I can complete the square here. X squared minus 10x is not a perfect square, but x squared minus 10x plus 25 sure is. So I'm going to add a 25 inside these parentheses. Wait, you can just do that? You can add a 25? No, but I can if I also subtract a 25. These first three terms form a perfect square. I got 0 equals y squared minus 24 times. Instead of x squared minus 10x plus 25, I'll write x minus 5 squared. I still have this minus 25. And then these ugly constants out here, 100 minus 26 squared. We'll get rid of this outer set of parentheses by distributing this negative 24. Maybe I jump up here. Got y squared minus 24 times x minus 5 squared. Negative 24 times negative 25. Let's see, 24 quarters is $6. So I guess that's plus 600. But I also have this 100, so I have 700 minus whatever 26 squared is. That entire mess is equal to 0. I'm getting pretty close to my desired form down here. My desired form, I left out an equals 1, by the way. To get that equals 1, let's add the constant over to the other side. I got y squared minus 24 times x minus 5 squared is equal to 26 squared minus 700. Divide both sides by whatever this constant is, and I'm done. Maybe so that I don't have to keep on writing it, I'll just call that thing c. I got y squared over c minus x minus 5 squared divided by what c over 24 is equal to 1. What I have is the equation of my hyperbola. I just realized while I'm editing this video that 26 squared minus 700 is actually a negative number, because 26 squared is 676. So c is a negative number, as is c over 24. So really, the standard form of my hyperbola should be x minus 5 squared divided by some positive constant minus y squared divided by some positive constant. Because it's the x term minus the y term, the parabola opens up horizontally, as I'll picture in just a minute. No real harm done, so I won't go back and re-record anything, but I wanted to add that comment. Anyways, back to the video. Playing the role of A is the square root of c over 24. Playing the role of B is the square root of c. Why do I care about what A and B are? Because plus or minus B over A always tells me the slope of the asymptotes. So in this case, I got the square root of c divided by the square root of c over 24 as the slope of the asymptotes. But I can simplify this a little bit. The quotient of square roots is just the square root of the quotients. If I think about the c on top as c over 1, I got c over 1 divided by c over 24. Divide fractions by multiplying by the reciprocal. I get c over 1 times 24 over c. The c's cancel out. I get the square root of 24. Let's see, the square root of 25 is 5, so the square root of 24 is roughly 5. If I draw two lines that go through the midpoint of A and B, so that's roughly here, right, 5, 0, with the slope equal to the square root of 24, so go up about 5 units each time you go over 1 unit, what I'll get are the asymptotes of this hyperbola. What I'm saying is we can kind of picture all of the points where this, new cell phone tower could be by drawing a hyperbola with this asymptote. Sure, good enough. If you don't like my drawing, we can come over here to Desmos, type in the equation, see the hyperbola in question. Note that we just want this arm on the right. Note that the point 6, 0 falls on this hyperbola. Here's y squared over c minus x minus 5 squared over c over 24 equals 1. If you want to see the asymptotes, just draw lines that have a slope of plus or minus the square root of 24 and shift them 5 units to the right. There's your asymptotes. Matches up pretty nicely with the parabola. Definitely a lot more than we needed for this problem, but it felt like a good idea to review a lot of these different topics rather than just be like, well, in this scenario, the answer is clearly a hyperbola and make a 15-second video.